Hello there, this is Shoot Socrates. Welcome to today's video where we will talk about indeterminate forms and L'Hopital's rule. That is how it is pronounced. It's like L'Hopital, L'Hopital's rule. It's obviously French and it kind of looks like hospital except there's no S and there's that funny accent sign. I think it's called a cravat or something like that above the letter O. It is French for hospital. Of course, it is named after a person, after a mathematician. So L'Hopital's rule is one of those things that hopefully years from now, you will still remember about calculus because it's one of those fun topics and I hope you enjoy it. It's one of those things that I really like talking about with my students. Okay, so first let's talk about indeterminate forms. Okay, here are two limits that hopefully you saw in basic calculus, right? So one of them says that the limit as x approaches 0 of sine x over x is 1. Okay, so what do we notice about this limit form? X is approaching 0, but sine of 0 is also 0. Okay, so the numerator and the denominator are both approaching 0. Okay, so in this case, we call this a 0 over 0 indeterminate form, or a limit of the form 0 over 0. Okay, so this is just a shorthand. Okay, there is still no such thing as 0 over 0. You cannot divide any number by 0, including 0. Okay, so it's just a shorthand. It has the form 0 over 0. Just because it's too long for us to say the denominator is approaching 0, the numerator is approaching 0. It's easier to just say it looks like 0 over 0. It has the form 0 over 0. Now, a little later on in calculus, you learned about horizontal asymptotes. Okay, we have also seen this in a recent video where we talked about limits at infinity. Okay, so if you don't remember that video, go back and check it out. So we said, okay, if you have a quadratic, let's say, divided by another quadratic, the degrees are the same in the numerator and the denominator. You can multiply and divide by 1 over x squared, okay? So you'll get 3 minus 5 over x plus 2 over x squared, and 6 plus 4 over x minus 1 over x squared. The two terms here, which has a 1 over x or 1 over x squared, they both go to 0 as x gets bigger and bigger, okay? So the limit is simply 3 over 6 or 1/2, okay? But in this limit, as x gets bigger and bigger, both the numerator and the denominator are also getting bigger and bigger. In other words, they're both approaching positive infinity, okay? So in this case, we call this an infinity over infinity indeterminate form, or a limit of the form infinity over infinity. Okay, so L'Hopital's rule is a way by which we can compute these limits. In the first limit, sine x over x, that became 1 because of the squeeze theorem. Okay, so in some cases, you don't have anything that powerful that helps you to compute a limit. So we're going to see L'Hopital's rule is a fun and powerful way to compute such indeterminate forms. Okay, so here's what L'Hopital's rule says. Suppose you have the limit as x approaches a of f of x is 0, and so is the limit as x approaches a of g of x, okay? So in other words, the limit as x approaches a of f of x over g of x is a 0 over 0 limit form, okay? L'Hopital's rule says that the limit as x approaches a of f of x over g of x is exactly the same as the limit as x still approaches x of the derivative of f divided by the derivative of g, okay? F prime over g prime, if this second limit exists. Similarly, if both numerator and denominator have a limit which is positive or negative infinity, the sign really doesn't matter, then the limit of the quotient is again the limit as x approaches a, the same number as the original limit, of the derivative f prime of x divided by the derivative g prime of x. Again, if this limit exists, okay? It doesn't have to be x approaches a. It can also be x approaches a only from the right or only from the left. Okay, L'Hopital's rule is still valid. Okay, little later we are going to encounter, I believe, 5 more indeterminate forms. So let me warn you ahead of time that L'Hopital's rule only applies to these 2 limit forms. 0 over 0 and infinity over infinity, plus or minus, doesn't matter. Okay, it does not apply directly to the other limit forms. Okay, we said that you have to compute the second limit and see that, make sure it exists. Well, you might still get 0 over 0 or infinity over infinity once you get the derivatives. Okay, so when that happens, you could try to apply L'Hopital's rule again and see if eventually you will get a limit that you recognize or something that you can compute easily by direct substitution. Okay, so let's take these formulas out for a test drive. All right, first example, let's find the limit as x approaches 0 of sine of 2x over tangent of 3x. Okay, so you may or may not have done this particular example in basic calculus. I know I would give something like this on the final exam, but maybe your teacher did not. Okay, so let's look for it. So as x approaches 0, sine of 2x is again approaching 0, and tangent of 3x is still approaching 0, okay, because x is getting smaller and smaller. Sine of 0 is 0, tangent of 0 is also 0. So this has the form of 0 over 0. Okay, so your teacher will probably say you should put down on the right something like 0 over 0 if you're about to apply L'Hopital's rule. Okay, so L'Hopital's rule says this limit is the same as if I take the derivative of the numerator and divide it by the derivative of the denominator. Okay, so don't forget the chain rule. The derivative of sine is cosine, but there's a 2x inside. So we have 2 cosine 2x in the numerator. In the denominator, the derivative of tangent is secant squared. But again, chain rule, there's a 3x inside. So 3 secant squared of 3x. Okay, so those are the derivative of the numerator and the derivative of the denominator. Okay, one more thing actually. L'Hopital's rule says f prime over g prime. Okay, it's not the quotient rule for derivatives. Okay, it is not f over g quantity prime. No, it's f prime over g prime. It's a lot simpler. Okay. All right. So can we take the limit now by direct substitution? X is approaching 0. Cosine 0 is 1, not 0 anymore. Secant of 0, secant is 1 over cosine. So that's also 1. All right. So therefore, our limit is simply 2 over 3 by direct substitution. Okay. So that limit is simply 2/3. Okay, next example. Limit as x approaches 0, x minus sine of x all over x cubed. Okay, so earlier we saw sine of x over x, but this is a little bit more complicated. We have x cubed in the denominator. X and sine of x both go to 0. Okay, as x goes to 0. So denominator goes to 0, numerator also goes to 0. Okay, so again, this is a 0 over 0 form. This has the form 0 over 0. Okay, so we are allowed to use L'Hopital's rule. We'll get the limit as x approaches 0, derivative of the numerator. Okay, derivative of x is just 1. Sine of x, we just did that a minute ago, so this is now cosine of x divided by the derivative of the denominator x cubed, so power rule, we get 3x squared. Okay. As x approaches 0, 3x squared still approaches 0. As x goes to 0, cosine 0 is 1. Okay, so the numerator is 1 minus 1. So that's 0. Okay, so this again has the form 0 over 0. So let's indicate that here again, just for good measure. Okay, so we can use L'Hopital's rule one more time. Okay, as I mentioned above, we said, yeah, you can try to do L'Hopital's rule repeatedly. See if eventually you get the limit that you recognize or where you can apply direct substitution. Okay, derivative of 1, 0, so goodbye. Derivative of cosine is negative sine, so this is going to be positive sine of x. And in the denominator, derivative is 6x. Okay, so, well, we did see this above. Okay, we said that sine of x over x has limit 1. So we can factor out the 1/6, and of course the limit is finally going to be 1/6. Okay, now what if you forgot years from now, 5 years, 10 years, like what is the limit again as x approaches 0 of sine x over x? But what if you remember L'Hopital's rule, which is more fun to memorize? It doesn't take much to memorize. Then you can do this one more time. Okay, what is so this again is 0 over 0. Okay, so we can apply L'Hopital's rule one more time, and we get derivative of sine is positive cosine. Derivative of 6x is just 6. Okay, again, cosine of 0 is 1, so this is 1 over 6. Of course, we should get the same answer either way. So speaking of memory loss, 5 years from now, you probably won't remember how to find this limit. Oh, you multiply and divide by something. But maybe you will remember L'Hopital's rule. Okay, so we said, right, as x gets bigger and bigger, that also gets bigger and bigger. So the limit is infinity, both in the numerator and the denominator. Okay, so that is a form of infinity over infinity. Has the form, this time, infinity divided by infinity. Okay, there we go. So, we can apply L'Hopital's rule. And these are just polynomials. So what could be easier? The derivative is 6x minus 5 over 12x plus 4. Okay, and once again, as x gets bigger and bigger, this is still going to infinity, and this is still going to infinity. Okay, but notice, of course, that it's a much simpler expression. Okay, so in this case, we feel like we are on the right track. Okay, so let's try it one more time. That has the form infinity over infinity, so we can apply L'Hopital's rule one more time. And so we get derivative of 6x minus 5 is just 6. Derivative of 12x plus 4 is just 12. So once again, we get the same answer. It is just 1/2, just like we saw earlier. Okay. Sometimes, unfortunately, L'Hopital's rule is not going to help us. Okay, so this example is very similar to something that we saw a couple of videos ago, where we did limits at infinity involving exponential functions. Okay, we had an example involving e to the 3x, e to the 4x, something like that, but I didn't make one for you involving general exponential functions, a to the x. Okay, but of course the principle is the same. Okay, if a is bigger than 1, a to the x is an increasing function. But if a to the x is smaller than 1, between 0 and 1, it's going to be a decreasing function. Okay? So what's going on here? X is going to positive infinity. So 2 to the x, 2 is bigger than 1, 7 is bigger than 1. 2 to the x is going to plus infinity. 7 to the x is also going to plus infinity. Here in the denominator, that's going to infinity. Oh, wait, this is also going to infinity. Maybe let's change that just for now. Let's change that to a plus. Okay, so we don't have dueling infinities. That will come a little later. Okay, so this has the form infinity over infinity. Okay, So if we can use L'Hopital's rule, and we'll have to take the derivative of the numerator and the denominator. Okay, so we can say that, whoops, grab the limit here. There you go. Limit has the form infinity over infinity. So we can apply L'Hopital's rule. What is the derivative of the numerator? Okay, so remember that the derivative of a to the x is a to the x ln of a. Okay, so we're going to get the same thing, but there's an extra ln of 2 in the first term. Similarly, we will have an extra ln of 7 in the second term. Repeat down here. That will be an ln of 2, and there will be an ln of 7 over here. Okay, in our last example, the quadratic became linear, the linear became constants. This is not heading in the right direction. Okay, that's still going to infinity, still going to infinity. Everything's blowing up to infinity. The ln of 2 doesn't help, just makes it bigger. So it's still infinity over infinity. So, well, can we try one more time? Yeah. Well, derivative of 2 to the x will give you another ln of 2. So now it's squared. And that's squared, and that's squared, and that's squared. It's not heading in the right direction. Okay? So L'Hopital's rule does not give us a limit form that we can compute by direct substitution or squeeze or one of the limit laws. So instead, yeah, we have to try something else. Sorry, this doesn't help. This dies, yeah. This doesn't help. It's more likely that we will die before we find the answer this way. We won't. Okay, so the key here is a to the x, right? We know the behavior of a to the x, okay? And we have two choices. We can either multiply and divide by 2 to the x, or multiply and divide by 7 to the x, okay? If we divide by 2 to the x, we will get 7 halves to the x here, but as x goes to infinity, 7 halves to the x still goes to infinity, okay? So we'll still get an infinity over infinity form, and yeah, sure, maybe we can use L'Hopital's, okay? But what about the other choice? What if we multiply and divide by 7 to the x instead? Okay, so this will go away, but we will have 2 over 7 to the x. Aha! 2 over 7 is now smaller than 1, between 0 and 1. So as x goes to infinity, 2 over 7 to the x goes to 0. Okay, so that might be a better option. Okay, so try again. We will have limit of this, but we will multiply and divide by a fraction. We will multiply and divide by 1 over 7 to the x. Okay, multiply and divide by 1 over 7 to the x. Okay, so 7 to the x will completely disappear. In the second terms, that's gone, and that's gone, but you will get 2 to the x over 7 to the x in the numerator and the denominator. Okay, so that's what happens in our first terms. And of course, we know the properties of exponential functions. When you have the same exponent, but two different bases, and we're dividing, you can take the quotient of the bases, 2 over 7, raised to the x. Okay, so we did not do L'Hopital's. All we did was some creative algebra. Okay, we chose 7 to the x instead of 2 to the x, because now we can see that because that base is between 0 and 1, as x goes to infinity, 2 7ths to the x goes to 0. Okay, this is a decreasing function, decreasing exponential function. as x gets bigger and bigger, this approaches 0. Okay, so therefore, by that principle, we will just get 6 over 9 as our limit, which is, of course, 2/3. All right, so that is our final limit. And just like in that video before, we can go to GeoGebra and graph this. I'll leave that up to you. Okay, check that as you go further and further to the right, you have a horizontal asymptote of y equals 2/3. Okay, so we started out by talking about indeterminate forms, and we saw the two basic indeterminate forms where we can apply L'Hopital's rule. Okay, 0 over 0 and infinity over infinity. So here are the two of the examples that we saw when we can directly apply L'Hopital's rule. There are 5 more limit forms which are indeterminate. Okay, so what are they? Okay, so here we have a product of two functions. Here we have a difference of two functions, and we have powers. Okay, so in an earlier video, we talked about general functions where both the base and the exponent of this exponential form have x in them. They both depend on x. So they are both functions of x, non-constant functions of x. Okay, what are we allowed to work with? Okay, one factor is approaching 0. The other factor is approaching infinity. Okay, in other words, one of the factors is getting smaller and smaller, but the other is getting bigger and bigger. Okay, so when you multiply them together, it's really not clear that the product is going to 0 or to infinity. Maybe it's going to something like 3 or 7 or pi. Okay, there's no reason why it should be infinity or 0. It could be just an ordinary real number. Okay, so that is why we use the word indeterminate. Okay, the opposite of determine. You cannot determine just by looking at the limit that, oh, the answer is going to be 7. Like, no, there's nothing that will tell you exactly what that limit is. Okay, we need something powerful, like L'Hopital's rule, except, once again, you cannot apply L'Hopital's rule to these kinds of indeterminate forms. Only these two kinds. Okay, next, we have a difference of two functions. So both of them are getting bigger and bigger. Remember where I changed the denominator in our last example so that instead of minus, it was a plus? Because minus doesn't really tell us, are you going to infinity or 0 or something else? But just by changing that sign, we kind of kept same ideas for the problem. Okay, so we're taking a difference. We have what is called an infinity minus infinity indeterminate form. Okay, so we're going to look at this a little later. We'll take a look at, well, what is the limit as x approaches infinity of 7 to the x minus 5 to the x. Okay, I didn't mention the example for 0 times infinity. As x approaches 0 from the right, x is approaching 0 from the right, still 0. But ln of x, as x approaches 0 from the right, ln of x is approaching negative infinity. Okay, so you have a limit of the form 0 times negative infinity. Okay, so again, the sign does not matter, only when we're computing the final answer. Okay, let's check out powers. Okay, so they all look the same, except what the base and the exponent are doing are different in each of these forms. Okay, so in the first form, both the base and the exponent are getting smaller and smaller. They're approaching 0. Okay, for example, as x goes to 0 from the right, sine of x goes to 0. The exponent, x, also goes to 0. Okay, so we have a 0 to the 0 form. Next flavor, the base is getting bigger and bigger, approaching infinity. The exponent is approaching 0, getting smaller and smaller. Okay, so here's something related to x times ln of x. What if we had ln of x to the power x as x is approaching 0 from the right? Okay, So we have ln that's approaching negative infinity, raised to the power x, that's approaching 0. I just realized we probably need an absolute value here. Okay, so just because we agreed that f of x to the g of x will be defined only if the base is positive. Okay, so we'll put absolute values over there later. So, final form, if the base is approaching 1, but the exponent is approaching infinity. Okay, so it's approaching, it looks like 1 to the infinity. And you might say, oh, wait a minute, isn't 1 to any power just 1? Okay, the problem is that the base is not exactly 1, it's only approaching 1. Okay, and the exponent is not 7 or 7 million, it's getting bigger and bigger. Okay, so here's an example we'll see in a few minutes. Okay, as x goes to infinity, we know 3x plus 1 over 3x minus 5, that's just approaching 1. Okay, if you don't believe me, do L'Hopital's rule. Okay, that's an infinity over infinity form. Derivatives are just 3 over 3, 1. Ta-da! So the base is approaching 1. The exponent is 2x, so it is also approaching infinity. Okay, so we have a 1 to the infinity form. Okay, so one more time. You can only use L'Hopital's rule when you have an indeterminate quotient, 0 over 0 or infinity over infinity. Not for products or differences or powers. Okay, but for a product form like this one, which we're about to do, what you can try is you can flip one of the factors into the denominator. Okay, you have two choices. Choose wisely. Remember that you're going to do f prime over g prime in the next step. So you probably want a g prime that is simple, easy to do. Okay, and again, we'll head you towards the right direction, something simpler instead of something more complicated. Okay, if you have any of those 3 power series, give it a name. I'm sorry, power series, power form. Power series comes later. Give it a name, set it equal to y, then take the ln of both sides. Okay, the power rule for logarithms says that the g of x is going to go down and you get ln of f of x. Okay, so again, you want to make sure that the f of x is positive. Okay, so if need be, there should be an absolute value. Okay, so when that happens, you will get a product of the form 0 times infinity, one way or another. Okay, because ln of infinity is infinity, ln of 0 from the right is going to be negative infinity. So all 3 forms are going to give you a 0 times infinity once you take the ln. Magic. Okay, for differences, infinity minus infinity, yeah, I wish you the best. I recommend that you try to do something creative, like perhaps multiplying and dividing by something or factoring out something, just like we did in an earlier example with, the 5 to the x, the 7 to the x, the 2 to the x, and all that. Okay, so let's find this limit as x approaches infinity of x squared e to the minus 3x. Okay, what's going on here? As x gets bigger and bigger, x squared is getting bigger and bigger, so that's approaching positive infinity. E to the minus 3x, okay, so that has a negative coefficient. E to the minus a big number is going to approach 0, okay? So this has the form infinity times 0. Okay, so let's set this up. We are going to get this limit. And we want to flip one of the factors into the denominator. Okay, so we're going to make a fraction. This is still limit as x approaches infinity. But we are going to flip one of these factors to the denominator. Okay, x squared will turn into 1 over x squared if that's our choice. But e to the minus 3x will simply become e to the 3x. So I think that is a better choice than x squared. Okay, so this time it's e to the positive 3x. As x gets bigger and bigger, e to the 3x is approaching plus infinity. Okay, so x squared is still approaching plus infinity. So this has the form of infinity over, where's my infinity? Infinity over infinity. Okay, so we can apply L'Hopital's rule to this quotient. Okay, again, don't do it directly here. There is no f prime times g prime. No, 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 no. Okay, take the derivative, so we get 2x, and the derivative here, 3e to the 3x. Okay, how convenient. What's going on now? X gets bigger and bigger, so that's still infinity, still infinity. So has the form infinity over infinity again. Okay, so we can apply L'Hopital's rule one more time, or as I sometimes jokingly say, we can hospitalize it one more time. So we get 2 over 9 e to the 3x. Chain rule one more time. Okay, so the numerator is now only a constant, and the denominator has the e to the 3x. So x is getting bigger and bigger. If you want, you can think of this as 2 over 9 e to the minus 3x, and we know that that just approaches 0. Okay, that's an indeterminate product for you. All right, let's do a couple of indeterminate differences. Okay, as x approaches infinity, 7 to the x is going to infinity. 5 to the x is also going to infinity. Okay, so we have two giants kind of pulling on each other, you know, like a tug of war. Who is going to win, the 7 to the x or the 5 to the x? Okay. Well, what can we do in this case? Try factoring something out. Okay, so again, we have two choices. We can factor out the 7 to the x or the 5 to the x. Okay, so again, in this case, factoring is essentially the same as multiplying and dividing by the same quantity. Okay, so we can choose to multiply and divide by either 1 over 7 to the x or 1 over 5 to the x. Okay, so if we chose 7 to the x, we will get 5 to the x over 7 to the x, which is a good thing, because as x goes to infinity, you are getting a base 5 over 7, which is between 0 and 1. So we saw earlier, that will go to 0. Okay, if you multiply and divide by 5 over x, you'll get 7/5 to the x, which will go to infinity. Okay, so word of advice, if you can work with 0 instead of infinity, I would go for the 0. Okay, it's easier to understand 0 than infinity. Okay, so it looks like the winner is going to be 7 to the x. Okay, so multiply and divide by 1 over 7 to the x. Okay, so we're going to do some manipulation here, some creative manipulation. In the numerator, we are going to bring the 1 over 7 to the x inside. Okay, so that will turn into 1, and you will have times 1 over 7 to the x times 1 over 7 to the x. Okay, but you have 1 over something. Okay, so we can flip that 7 to the x back into the numerator. Okay, so this simply becomes times 7 to the x. Okay, so yeah, if you don't believe me, distribute this 7 to the x inside. These will cancel, these will cancel. You're back to 7 to the x minus 5 to the x. Okay, so simplify further. We're going to get 7 to the x times 1 over 7 to the x. That's just 1. And we said that this is going to turn into 5 to the x over 7 to the x. And one more time, I'm not going to waste a line. We can put these together as 5 over 7 to the power of x. Okay, so do we have something better now? Okay, that's the million-dollar question. 5 over 7 to the x will approach 0 as x goes to positive infinity, because that's between 0 and 1. Okay, so that approaches 0. So the base approaches, I'm sorry, this expression just approaches 1. Okay, we're multiplying though by 7 to the x. Okay, so this is 1, this is approaching 1, this is approaching infinity. Okay, and you might say, well, wait a minute, isn't that one of the indeterminate forms? No, it's 0 times infinity. Okay, this is 1 times infinity. Okay, it's not on the table because it's not an indeterminate form. Okay, what is this saying? This term, this factor, is getting closer and closer to 1. Okay, but this factor is getting bigger and bigger. Okay, so 1 times a big number is still a big number, right? So that limit is going to be positive infinity. Okay, you can of course just write it as infinity, or you can emphasize by saying positive infinity. All right, here's another indeterminate difference. Okay, we're approaching 0 from the right positively, and we're looking at cosecant x minus cotangent x. Okay, I like this example because we don't often work with cosecant or cotangent. Okay, so let's put them together. They're saying like, what about us? Why are you ignoring us? Okay, so remember that cosecant is 1 over sine, and cotangent is cosine over sine. So both of them we're dividing by sine. Okay, and as x approaches 0 from the right, sine of x stays positive, but it's getting smaller and smaller. So you're in danger of dividing by 0. It's getting bigger and bigger. Okay, so if you don't believe me, well, maybe you will believe Maple. What is the cosecant of 0.01? Okay, that's radians. Okay, so Great Maple, it is about 100. Ooh. Okay, so similarly, cotangent, you have cosine over sine. And if you plug in a small number, the denominator is close to 0. Okay, so what are you? Ooh, 99.996. Okay, so they're close. Okay, so it looks like when you take the difference, even though this is getting bigger and bigger, this is not that far behind. Okay, so maybe the limit is, I don't know. Maybe it could be 0. We'll see. Okay, so it's a difference. Okay, so once again, you are not allowed to use L'Hopital's rule on a difference. Okay, but we said cosecant is the same as 1 over sine. Okay, so we'll replace that with 1 over sine of x, and cotangent is cosine over sine. So we'll replace that with cosine x over sine x. Okay, so it looks like the obvious thing to do would be to combine the two fractions. I mean, they do have the same denominator, don't they? So we can write it as 1 minus cosine x, just the numerator. We'll put them together here. And there you go. Now it's just one fraction. 1 minus cosine x all over sine of x. Okay? All right. So x is approaching 0 from the right. Sine of x, again, getting close to 0. But what about 1 minus cosine x? Well, we saw something like that a little earlier when I believe we did x minus sine of x, I believe. So, yeah. That is also going to 0 because cosine of 0 is 1. You get 0 is 0. So this has the form 0 over 0. Great. So we can apply L'Hopital's rule, and we will get in the numerator, déjà vu, we did this, right? Derivative of negative cosine is sine of x. The derivative of sine of x, this part we didn't do, is cosine of x. Okay. So now, is it still 0 over 0? Well, that's 0, but cosine 0 is 1. Okay, so by direct substitution, we will get 0 over 1, which is equal to 0 by direct substitution. All right, so in this case, the strategy is simply combine with a common denominator. Then you can apply L'Hopital's rule, and we get 0, which is verified by our numerical data. 100.001 minus 99.996. That difference is very, very small. Okay, our last example is going to be an indeterminate exponential form. Okay, so once again, I said this earlier, but I did not write it down. So I said the limit of the base, 3x plus 1 over 3x minus 5, as x gets bigger and bigger, goes to infinity. Well, we can use L'Hopital's rule for this. This has the form infinity over infinity. So this is the limit of 3 over 3. The derivative is simply 3 in both the numerator and the denominator. So that's just 1 by L'Hopital's rule. So I'll just abbreviate it like that. Okay, so the base is approaching 1. The exponent 2x is getting bigger and bigger. So thus, this function has the form of 1 to the infinity. Okay, again, that's just a shorthand. Okay, it is not literally 1. It's not literally infinity. Okay, it's just getting, the base is just getting closer and closer to 1, but the exponent is getting bigger and bigger. Okay, so earlier we plugged in 0.01 into cosecant, cotangent. Let's plug in a big number into this exponential expression. Okay, so let's copy that and let's ask, oh great maple, what happens if you plug in 100 into this function? Okay, so actually, you know what, let's do it by hand. Okay, because 100 is an easy number. 301, 300 minus 5 is 295. So that's 301 divided by 295. Okay, so I hope you can see that is pretty close to 1. Okay, but we're raising it to the power 2 times 100 to the power 200. Okay, so this is not exactly 1. This is definitely not infinity. It's just a big number. Okay, so great maple, can you simplify, can you crunch that out for us? Ooh, it's about 56. So it's not 1. It's not exactly very big either. 56, that's not exactly a big number. Okay, so what if we add another 0 here? Okay, you'll get 3001 over 2000 and blah, 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 raised to the power 2000. Oh, great maple. Ooh, it actually got smaller. How can that be? Ooh, well, that's math for you. You never know what's going to happen. Let's add a couple more zeros. 10,000, 100,000. That will look great in my bank account. That will give us, and let's give it a minute. Oh no, I broke maple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me just put it out of its misery. Oh no, I broke maple. That's okay. We don't have to plug in 1 million. So we'll just stick to something a little bit more reasonable. So we saw that if you plug in 1,000, you'll get something not so big, not small either, but looks like just an ordinary number. Okay, so what do we do to find this limit? Okay, and our answer should be close to 55 something. The suggestion was, give this expression a name. Let's call it y. And then we'll take the ln of both sides. Okay, so ln of y is ln of this exponential expression. And we know from properties of logarithms that we can drop the 2x, and then it becomes 2x times ln of 3x plus 1 over 3x minus 5. Okay, so the 2x has dropped out. Okay, so this is now a product form. As x gets bigger and bigger, 2x is getting bigger and bigger, so that's approaching infinity. But we said that this has limit 1, so ln of 1 is 0, okay? So this is an infinity times 0 limit, which is an infinity, where is my infinity? There you are, times 0 form. Okay, so now we can apply L'Hopital's rule as x gets gets bigger and bigger, goes to infinity. Okay, so instead of let's recall. If you have an indeterminate product form, you have to flip one of the factors to the denominator. We have two choices: either flip x or flip ln of 3x plus 1 over 3x minus 5. I would not flip the ln factor. Okay, that would be a very bad choice. Okay, x simply becomes 1 over x if you flip it to the denominator. Okay, so let's do some algebra first. Okay, we can keep the 2 outside, and we will turn this into a fraction. We'll put it in the numerator. And in the denominator, we will put the x. Okay, so the x turns into 1 over x. Okay, so this is still approaching 0. ln of 1 is 0. But now 1 over x, as x gets bigger and bigger, that goes to 0. Okay, so this is a 0 over 0 form. Okay, so we are now allowed to apply L'Hopital's rule. Okay, however, before we do that, let me show you a little trick. We already know that the numerator has limit 0. Okay, that's not going to change if we apply one of the properties of logarithms, which I hope you recognize. It's just the quotient rule for logarithms. Okay, so we can turn the numerator into ln of 3x plus 1 minus ln of 3x minus 5. Okay, so it'll be a minus something, and the 3x plus 1 is all by itself now, and I can copy that and turn it into 3x minus 5. Okay, so that was just algebra. Okay, every step so far that we've done is algebra, manipulations. Okay, so that's why these properties of exponential functions, logarithms, they're all coming together in this example, basically. Okay, and you might think, oh, wait a minute, isn't that now infinity minus infinity? No, it came from this. Okay, so it's still a 0. It's still approaching 0. Okay, so now we can apply L'Hopital's rule. Okay, so we're going to take the derivative of the numerator and the denominator. Instead of writing the limit symbol, I am going to use a right arrow here, which means approaches. Okay, so that right arrow takes the place of limit as x approaches infinity of blah, blah, blah. Okay, so we can apply L'Hopital's rule. We can leave the 2 outside. ln of 3x plus 1. Okay, derivative of ln of something is 1 over something. And then chain rule, we need the derivative of 3x plus 1. Okay, so we need a fraction, 1 over something, 1 over 3x plus 1. Okay, so we can erase this. Okay, times the derivative of 3x plus 1, which is 3. Okay, so we can just put it in the numerator. Now, minus derivative of ln of 3x minus 5, same thing. 1 over 3x minus 5 times the derivative of 3x minus 5, which is again 3. Okay, so it's going to be just like the first term, except we have 3x minus 5 in the denominator. Okay, but now this is our main denominator. Okay, so we need the power rule. What is the derivative of 1 over x? That's the same as x to the minus 1. X to the minus 1, you drop the minus 1, and then subtract 1 from minus 1. Minus 1 is minus 2, not 0. Okay, so we have negative x to the power negative 2. Okay, so let me just annotate here by applying L'Hopital's rule. Okay, but now we have more algebra that we can do. So we have 2 here, and then, well, we have negative x to the minus 2, but it's not in the denominator. We see 1 over negative x to the minus 2. So that is simply negative x to the power 2. Okay, we put it back into the numerator because that's a negative exponent in the denominator. Okay, so in the numerator we have this. Let's copy that here, and let's put brackets. Okay, should we factor out the 3? Yeah, we can do that. You want to do that? Sure, let's do that. Okay, so we got 6 over here times negative x squared. So let's just write it as negative 6x squared. Okay, so this is now a 1, and this is also a 1. Okay, but now we are going to, well, let's put these two fractions together. So we get 1 times 3x minus 5. So we are going to multiply this first numerator by 3x minus 5. But this we will multiply by 3x plus 1, which is over here. And this is where you have to get really careful, okay? Because we have 3x minus 5 minus quantity of 3x plus 1. Okay, so am I going to have enough room here? Oh yeah, I still have room. Okay, Maple will sometimes scroll me off the page as I'm about to see. Ooh, we still have a little bit of room. So this is 3x minus 5 minus 3x minus 1. Okay, not plus 1, minus 1. Okay, that minus has to be distributed to the 3x and the plus 1. That's minus 3x minus 1. Okay, so the 3x's cancel and you get minus 6. Okay, minus 5 minus 1. That is minus 6. Okay, I'm going to try to see if I can get away with one more line. Oh, okay, Maple is being kind to me today. Okay, so that's going to be minus 5 minus 1. Okay, so we said that's minus 6. Okay, so let's just complete it over here. Minus 6x squared times minus 6, that is positive 36x squared. And whoops, oh, check it out. I made a bad mistake here. This 3x plus 1 has a partner down here. Okay, we combine fractions. Okay, so that is a common denominator of 3x plus 1 times 3x minus 5. Okay, so that should also be our denominator over here. Okay, and that's very important because look what's happening. Okay, so that limit, that fraction is 3x squared, 36x squared over 9x squared something. Okay, so that's back to our almost first example where we have a quadratic over a quadratic. We had something like 6x squared over 9x squared, something like that, or was it 3 and 6? I forget. But bottom line, it's a quadratic over a quadratic. 36x squared over 9x squared in smaller terms, that limit is simply 36 over 9. Okay, so I'm going to put another arrow symbol and let me scoot out of the way here. This is going to go to 36 over 9. And of course, that is simply equal to 4. Okay. And we think, okay, great. The answer to our limit is 4. But wait a minute. Oh, no, it better not be 4 because it looks like it should be more like 54 or maybe 55. Okay. So what happened here? Well, that's because we took the ln of both sides. Okay. And it's the new right side where we found the limit. Okay. So algebra, ln of y is approaching 4. What did I tell you? It knocked me out of the screen. Okay. So bottom line, ln of y is approaching 4. Okay, so I need my arrow. So by continuity, okay, if the ln of a number is approaching 4, then that number must be approaching, is it ln of 4 or is it something else? It should be, I'm sorry, y is approaching e to the power 4. Okay, so remember that ln, if you don't like that limit symbol, think of it as an equation. ln of y equals 4 means that y equals e to the 4. Okay, so since ln is continuous, you can say that if ln of y is approaching 4, then by continuity, y must be approaching e to the power 4. Okay, and is that close to 54? Keep your fingers crossed. And what are we gonna get? Yep, it's about 54.6. Okay, so that gives us confidence that our limit is correct. So I hope you enjoyed that video. I hope that years from now, you will remember L'Hopital's rule and what fun you had doing your homework with it. Okay, so until next time, I hope you enjoy the rest of your day. Bye.